Can a moon be smashing into its planet's rings right now? It turns out it is possible. In the vast reaches of the Saturnian system, the moon Iapetus is relentlessly ploughing through a diffuse torrent of cosmic dust, a hidden ring so immense it dwarfs all others. This ongoing collision isn't a spectacular crash of worlds, but a subtle, inexorable barrage that has painted one half of Iapetus in shadows and reshaped its very form. Some epochs, it accumulates the debris like a silent collector, and in others, the impacts reveal deeper enigmas. This is the ultimate cosmic embrace, but as we unravel its mechanics, Iapetus's secrets only multiply. That is because Iapetus endures a perpetual onslaught, one hemisphere bombarded by dark particles, the other spared in radiant purity. Across its waste, a monumental barrier rises, a ridged scar from ancient forces, whose ties to this dusty assault challenge our grasp. Why does this moon bear the marks of such a dramatic, ongoing encounter? What primordial chaos or gradual, relentless mechanism could have forged a pathway through the rings, altering a world forever? And what revelations does this far-flung sentinel offer about the violent birth pangs of our solar system? Join with me today as we venture to Iapetus, Saturn's third largest moon, and arguably its most beleaguered. Our tale commences with the discerning gaze of Giovanni Domenico Cassini. In 1671, employing the refracting telescopes of the Paris Observatory, Cassini identified a fresh speck of light circling the banded colossus. Yet this novel moon exhibited peculiar conduct. When positioned on the western flank of Saturn in its circuit, it shone adequately, but as it migrated to the eastern flank, it appeared to dissolve, growing exceedingly dim, frequently eluding detection altogether in those instruments. Contemplating his sightings, Cassini noted that at times after commencing to fade with the 32-foot telescope, it has been hunted fruitlessly the following day with one of 45 inches. Cassini inferred that this moon possessed one half markedly dimmer than the other, and it was tidally bound to Saturn, perpetually orienting the same visage toward its host, akin to how our own moon faces Earth. This implied that as Iapetus circles Saturn, it switches between displaying its luminous face and its shadowed face toward our world. When the luminous side confronted us, on the western side from our vantage, it was observable. When the shadowed side confronted us, on the eastern side, it receded into obscurity. It was a remarkable deduction for the 17th century and signified the inaugural surface trait discerned on a planetary satellite beyond the Earth-Moon duo. Cassini dubbed the four moons he unearthed Sidera Laodicea, Stars of Louis, to honor King Louis XIV. But these designations faded. Subsequently, John Herschel proposed titles from the Titans, siblings of Saturn in law. Iapetus, progenitor of Atlas and Prometheus, and thus ancestor of Prometheus's progeny, humanity, emerged as the appellation for this odd realm. For ages, Iapetus lingered as scarcely more than a luminous point, manifesting this eerie luminosity fluctuation. Even the Voyager spacecraft, which transformed our comprehension of the outer solar expanse in the late 1970s and early 1980s, secured only remote passages. Voyager 1 seized visuals depicting the harsh luminosity disparity, affirming Cassini's surmise, but the clarity fell short of disclosing the elaborate particulars. Voyager 2 performed marginally superior, traversing nearer and affording us our initial alluring peek at another astounding attribute, a suggestion of an enormous crest proximate to the equator. But the complete vista, the awe-striking oddity of Iapetus awaited the advent of a committed Saturn investigator. Enter the Cassini spacecraft, aptly titled after the Moon's finder. Reaching Saturn in 2004, the Cassini endeavor would devote 13 years to disclosing the enigmas of the ring behemoth and its varied lunar kin. And Iapetus ranked prominently among its objectives. Cassini's examinations, especially approximate, directed passage in September 2007 that positioned the craft a mere 1,640 kilometers from Iapetus's facade, metamorphosed the Moon from a remote sparkle into an intricate domain we could ultimately scrutinize. Iapetus is a moon of modest density, merely 1.2 times that of water, implying it comprises up to 75% water ice. Its contour deviates from perfect sphericity, partly owing to the equatorial crest, imparting it that characteristic flattened, nut-like semblance. It probably lacks a subterranean sea like Enceladus or Europa, given the absence of signs of fresh geological vigor or the tidal warming required to sustain liquid water beneath its frozen mantle. Its exterior is archaic, frigid, and densely pitted, especially in the luminous zones of Roncevaux Terra, bearing witness to eons of assault. Its path is likewise anomalous. Iapetus circuits far beyond other Saturnian satellites at a mean span of roughly 3.5 million kilometers, exceeding twice the interval of the subsequent primary moon, Titan. This expansive gap signifies it requires 79.3 Earth days to fulfill one loop around Saturn. Vitally, its path is also notably slanted, inclined by approximately 15.0 degrees comparative to Saturn's equatorial level, where most other chief moons travel. This remoteness indicates Iapetus experiences lesser influence from Saturn's magnetic envelope and the fierce radiation zones nearer the planet. Its path's tilt could hint at its genesis or early relocation saga, conceivably suggesting it didn't coalesce within the identical equatorial plateau as Saturn's nearer, orderly moons. But let's pivot to the facet of Iapetus that renders it so captivating to behold: its ongoing collision with Saturn's outermost rings. Iapetus is neatly bifurcated into two discrete domains, a direct consequence of this ceaseless smashing. The forward hemisphere, the facet that confronts ahead as Iapetus circuits Saturn, is profoundly obscured. This domain is termed Cassini Regio and envelops about 40% of Iapetus's exterior. Its reflectivity, the gauge of how much radiance it rebounds, is extraordinarily meager, between 0.03 and 0.05. That's as somber as tar or soot. It engulfs nearly all the solar glow that alights upon it. In sharp opposition, the rearward hemisphere, the facet oriented away from the orbital direction alongside the poles, is extraordinarily radiant. This domain, including Roncevaux Terra northward and Saragossa Terra southward, flaunts a reflectivity of 0.5 to 0.6, as brilliant as newly descended snow or lustrous water ice. This nearly 10 times variance in reflectivity stands as the most extreme interhemispheric contrast we recognize in the solar system. Envision witnessing this realm intimately. One side a profound reddish-brown or ebony, the other a blinding white. In certain sectors, notably near the equator, the demarcation between these halves can seem strikingly acute, as if etched deliberately. In other sectors, particularly at elevated latitudes, the shift is more progressive, with luminous rayed depressions scattered over the somber terrain. This portrayal from Cassini starkly illustrates the disparity. It is a realm veritably cleaved in twain. So what provokes this yin-yang visage? And how does it tie to Iapetus smashing into Saturn's rings? For an extended period, the dominant notion posited an inner source, perchance some variety of obscure cryovolcanic substance surging from Iapetus's core and overlaying one side. A document assessing the Voyager data from Bradford Smith and Associates in 1981 contended for this notion, pinpointing a ring-like form as a depression partly inundated with somber, eruptive substance as bolstering proof. Nonetheless, Cassini's radar and depiction data disclosed that the somber substance constitutes a comparatively slender stratum, perhaps mere tens of centimeters to a meter thick in most locales. Moreover, collision depressions within Cassini Regio frequently unearth radiant, icy substance from beneath, penetrating the somber overlay. This potently indicated the somber material wasn't surging upward from below, but was being laid down from above. A document from 1982 conducted spectrophotometric examinations of the somber forward exterior and determined that the makeup of the substance was carbonaceous, akin to that of the Murchison C2 meteorite, which descended to Earth amid a deluge in 1969. To elucidate this discovery, the authors directed attention to prospective offenders near Iapetus, within the Saturn arrangement. The chief suspect, debris from Saturn's external erratic moon, Phoebe. Phoebe is a comparatively sizable, somber moon, ensnared by Saturn's pull, circling the planet in the incorrect direction, a retrograde path, at a vast remove. Across billions of years, collisions on Phoebe and other diminutive, somber, retrograde moons have propelled a broad, sparse platter of somber dust, granules. The sun's emanation applies force on these dust granules, inducing what is recognized as the Poynting-Robertson phenomenon. Consequently, this dust coils inward towards Saturn, likewise progressing in a retrograde manner. Now, returning to Iapetus, it circuits Saturn in a prograde direction, the identical direction as Saturn's spin and most other moons, but its path is considerably farther out than the principal rings and nearer moons. As it voyages around Saturn, its forward hemisphere fundamentally rams directly into this approaching current of retrograde somber particles stemming chiefly from the Phoebe cluster. It's akin to navigating through a horde of insects. They predominantly splatter on your frontal shield. The rearward hemisphere, safeguarded by the moon itself, amasses far less of this somber substance. This ceaseless smashing into the dust, part of what we now know as the Phoebe ring, Saturn's most expansive and elusive ring system, is the core of Iapetus's transformation. Discovered in 2009 by the Spitzer Space Telescope, the Phoebe ring spans an astonishing breadth, extending from about 128 to 207 times Saturn's radius, a colossal halo of microscopic particles invisible to the naked eye, but detectable in infrared. This ring isn't a dense band like the iconic A or B rings. It's a tenuous cloud, born from micrometeoroid impacts on Phoebe and its kin, ejecting material that then succumbs to solar radiation pressure and spirals inward. Iapetus, orbiting at around 59 Saturn radii, lies in the path of this inward-migrating dust stream. Every moment, as Iapetus hurtles through space at orbital speeds exceeding 3 kilometers per second, it collides with these particles, which embed themselves into its icy surface. Over geological timescales, this accumulation has built up the dark coating on the leading side, turning it into a cosmic dust trap. But mere accretion doesn't wholly account for the profundity of obscurity we observe on the forward side of Iapetus, or the intricacy of the frontier between somber and radiant. This is where thermal partitioning and water ice vaporization enter the fray. The somber substance deposited on the forward hemisphere imbibes more sunlight than the encircling radiant ice. This prompts the surface warmth to ascend marginally. Iapetus is extraordinarily chilly, but even a minor warmth increment suffices to induce the volatile water ice to vaporize, converting straight from solid ice into water vapor. This vaporizing water vapor doesn't simply evaporate. Owing to Iapetus's exceedingly languid rotation, its day spans about 79 Earth days, aligning with its orbital span, diurnal temperatures are elevated, and the ice has ample duration to vaporize away from the warmer, somber zones. Indeed, vaporization on Iapetus is so swift that if its exterior were unadulterated ice, we would witness over 100 meters of ice forfeited to vaporization in 1 billion years, swifter than any other Saturnian companion. But where does the ice migrate? It preferentially re-solidifies and congeals onto the chilliest accessible exteriors. These are the already radiant, icy domains on the rearward hemisphere and near the poles, which rebound more sunlight and remain cooler. Scholars propose that, due to its negligible ambience, vaporizing molecules pursue ballistic paths, leaping remarkable distances to the rearward hemisphere in the manner of a projectile. This engenders a runaway affirmative feedback cycle. Somber zones grow slightly warmer, forfeit their ice, become even more somber as the underlying somber dust concentrates, imbibe even more warmth, and vaporize more ice. Radiant zones remain chill, gather migrating frost, become even more radiant, rebound more sunlight, remain even chillier, and gather more frost. Across millions and billions of years, this mechanism has radically honed the boundary between the somber forward hemisphere and the radiant rearward hemisphere, culminating in the extreme disparity we behold today. Thus, the grand division appears to be a fusion of external contamination from the Phoebe ring's dust and an internal classifying apparatus propelled by sunlight and ice vaporization, a profoundly extraordinary exemplar of celestial dynamics in action, where a moon's perpetual smashing into ring debris sculpts its destiny. But the dual-hue pigmentation is merely a fragment of Iapetus's eccentricity, intertwined with its ring encounters. As Voyager 2 intimated and Cassini verified in breathtaking precision, Iapetus harbors another trait unparalleled in the documented solar system, a titanic equatorial ridge. This ridge is essentially a barricade of peaks, extending for around 1,600 kilometers, at least midway around the moon's girth. On average, it measures about 200 kilometers broad at the foundation and attains soaring elevations of up to 20 kilometers above the adjacent landscape. That's considerably loftier than Mount Everest. And the most perplexing aspect? It traces the equator nearly flawlessly, mainly restricted within the somber Cassini Regio, though additional equatorial elevations spotted by Voyager on the rearward hemisphere might represent a prolongation of this edifice. In depictions like this one, captured by Cassini, during its intimate passage, the magnitude is overwhelming. It bestows Iapetus a distinct walnut configuration. What could have conceivably molded this girdle of peaks, and does it connect to the ongoing ring smashing? This ranks among the foremost persisting riddles of Iapetus. Numerous suppositions have been advanced, each with its merits and flaws. One principal concept posits the ridge as a vestige of a far swifter rotating history, potentially influenced by early dust accumulations from the nascent Phoebe ring precursors. Contemporary simulations have indicated that early in its chronicle, soon after formation, Iapetus may have revolved much more hastily, perhaps concluding a rotation in around 16 hours. This rapid whirl would have augmented flattening, causing the Moon's equatorial sectors to protrude outward due to centrifugal impetus. While the Moon remained youthful and comparatively malleable or partly liquefied, as Iapetus chilled and hardened, this equatorial protrusion solidified in situ. Later, gravitational interplays with Saturn decelerated the Moon's rotation over millions of years until it grew tidally bound, revolving only once per circuit, 79 days. As it slackened, the centrifugal impetus upholding the protrusion waned, but the now rigid crust couldn't entirely revert to a sphere. The substance basically slumped downward, heaping up near the equator to form the massive ridge we perceive today. This supposition aligns well with the ridge's equatorial placement and its archaic, densely pitted appearance, implying it arose very early. However, it necessitates Iapetus to have whirled extraordinarily fast, possibly nearing its structural disintegration velocity, and to have hardened, while preserving that protrusion, perhaps exacerbated by heavy dust infall from the forming ring system, adding mass unevenly. Another compelling supposition suggests that the ridge stems from substance cascading onto Iapetus from an extrinsic origin, specifically the disintegration of a sub-satellite or a ring arrangement that once encircled Iapetus itself, potentially seeded by the same dust streams from the Phoebe ring. If Iapetus harbored a debris ring early in its chronicle, perhaps derived from a seized entity or a massive collision, this substance would inherently circuit above its equator. If this ring grew unstable, or if Iapetus shifted slightly in its path, the ring substance may have been thrust just beyond the Roche threshold, the juncture where the tidal influences of a large body overpower the inner gravity of a smaller one. This may have prompted ring substance to gradually precipitate onto the exterior of Iapetus, accumulating preferentially along the equator. This could potentially clarify why the ridge appears most salient on the somber forward hemisphere if the ring substance itself was somber, or its deposition aligned with the influx of somber dust from the Phoebe ring. Some simulations indicate that even a modest moonlet, fragmenting within Iapetus's Roche threshold, could furnish sufficient substance. While graceful in elucidating the locale, the precise apparatuses for forming and then collapsing such a ring remain contested, especially in light of the broader Phoebe ring's dynamics, where dust continues to rain inward, possibly echoing ancient, more intense episodes. Other notions, such as tectonic mechanisms or convective surging from the interior, falter in explaining why the activity would be so narrowly confined to the equator over such an immense expanse. A colossal impact is also improbable to yield a long, linear, and impeccably equatorial trait. Cassini's meticulous depictions reveal the ridge is densely pitted, confirming its primordial roots. It seems structurally comprised of icy crustal substance. Some portions exhibit proof of avalanches and collapse traits. Whatever the procedure, it must have transpired very early in Iapetus's chronicle, perhaps within the initial few 100 million years of the solar system's formation. The ridge endures as a monumental relic from Iapetus's turbulent adolescence, a petrified chronicle of forces we are still endeavoring to comprehend, possibly amplified by the Moon's eternal smashing into the ring's detritus, which may have provided the raw materials or triggered the instabilities. Beyond these features, the ongoing interaction with the Phoebe ring holds profound implications for our understanding of the solar system's moons. This diffuse ring, the largest known in our celestial neighborhood, exemplifies how even distant, captured objects like Phoebe, likely a wanderer from the Kuiper belt, snared by Saturn's gravity billions of years ago, can influence inner worlds. The dust's retrograde spiral, driven by the subtle push of sunlight, illustrates the delicate balance of forces in planetary systems, where radiation pressure can reshape surfaces over eons. Iapetus, as the unwitting collider, serves as a natural laboratory for studying these processes, revealing how exogenic materials can dominate a moon's evolution, masking its original composition and driving thermal migrations that echo climate feedbacks on Earth, albeit in the vacuum of space. This smashing isn't a cataclysm, but a slow symphony of particles, each collision a whisper from the solar system's youth. When debris disks were denser, impacts more frequent, and moons like Iapetus bore the brunt of cosmic migrations. It prompts us to ponder the fragility of worlds, how a moon, isolated in the cold expanse, can be forever altered by invisible streams, reminding us that space is not empty but alive with motion, where every orbit intersects hidden currents. In this dance, Iapetus embodies resilience amid assault, its scarred face a testament to survival in a universe of constant change, urging us to reflect on our own planet's vulnerabilities to cosmic whims. So, what do we comprehend about Iapetus and its perpetual smashing into Saturn's rings? More than previously, but less than we crave. The Cassini mission radically altered our perception of this enthralling moon. Its intimate passage supplied the data that cemented the exogenic dust and vaporization theory for the moon's dual visages. It furnished astonishing, high-clarity views of the equatorial ridge, permitting detailed examination of its architecture and form, even if its genesis stays debated. Cassini gauged Iapetus's contour, gravitational domain, and surface makeup with unparalleled precision. The 2009 revelation of the Phoebe ring by Spitzer complemented this, providing the missing link to explain the dust source, transforming our view of Saturn's ring system from confined bands to a sprawling, dynamic envelope that ensnares moons in its grasp. Without these explorations, Iapetus would have persisted as the faint, bewildering speck it was for centuries, and yet myriad enigmas linger. What is the precise interplay between the Phoebe ring's dust and the ridge's formation? How has the ring evolved over time, and could intensified dust fluxes in the past have triggered greater cataclysms on Iapetus? What exact compounds lurk in the dark veneer, beyond mere carbonaceous hints, and how do they mirror the primordial materials of the outer solar system? Unless we return there, with landers to sample the dust-laden ice, or orbiters to map the ring's currents in real time, certainty will elude us. No ventures are presently scheduled to probe or even encircle this besieged bastion, so for now we observe from afar, as the smashing continues, unabated, which feels fitting. After all, as I alluded at the outset, Iapetus is engaged in the ultimate cosmic collision course, and the universe seldom unveils its rhythms without a struggle. Thanks for watching this video.